Morning, everyone. This is the John Chappell Natural Philosophy Society Science Chat. And so, Bob, you said you had some slides you'd like to show us?
Sure. It's an update on some things that I've learned over the last couple of weeks on classical electrodynamics. I'll try to keep the math to somewhat of a minimum. I'm not going to drive anything, but some topics in classical electrodynamics that I wanted to make people aware of because I'm not sure if people are aware. So let me share my screen. Share screen. Share screen. Share. Share audio, entire screen.
Yeah, you have to make sure you share entire screen.
Yeah, but it's not highlighting the share. It's only highlighting cancel.
Well, you do have to click in the middle of the screen where it says share all screen.
Ah, okay.
There you go. Okay, we think I see your screen here. I'm going to add that to the stream. Okay. There we go. An update on classical electrodynamics research.
Okay, so if I do, let me see, slideshow. Can you see the whole screen?
Yeah, we can see the whole screen now.
Okay. So this is an update on my research in classical electrodynamics. And what I am looking for is the simplest and most complete approach for deriving classical electrodynamics. And so I've summarized what I mean by Maxwell's system for electrodynamics. I think I actually presented this slide once before to you folks. Just equations 1 through 4 is Maxwell Heaviside version of Maxwell's equations. Not going to go into a lot of that. So my approach has been to look at Weber electrodynamics. Weber electrodynamics is traditionally not presented as a field theory. This approach assumes just one potential energy function. And from that, you get all of classical electrodynamics or Weber's classical electrodynamics.
So how could that not be presented as a field?
Right, but they say no fields in traditional Weber electrodynamics. So I don't know if you can see my pointer.
I thought
at the F. At the F, the force is equal to this equation in Weber electrodynamics. And what I do is just take all that stuff and define a field, E. Okay, so from this one equation, this potential energy equation, I define and derive fields and potential functions for Weber electrodynamics. And it's also, this research has also highlighted to me some issues with the regular Maxwell system of equations. So here's what I came up with the Weber field approach to classical electrodynamics. These equations 1 through 4 look very much like Maxwell's equations, but the interpretation is a little different. Not going to go into any of these today. Just want to review what I think I've already presented here many weeks ago. But anyway,
what's the vector R? Sorry, just in the last vector R, you have 2, 3.
I have 3 of them, and these come about because down here under R1, I don't know if you can see that.
Yes.
It's a derivative of the current density, I'm sorry, the charge density function rho. That does not appear in Maxwell's equations. For some reason, it looks like, and this is why I say this approach has highlighted for me what I think are issues with Maxwell's equations, Maxwell's approach. And Maxwell's approach, for some reason, doesn't have these time dependent of the charge density function, whereas Weber's approach does. And so you introduce these additional R's, R1, 2, and 3. So, but if you set these time derivatives of the charge density function equal to 0, then R1, 2, and 3 go away, and it looks just like Maxwell's equations. The interpretation is still a little different, but that's what R is.
Okay.
Anyway, what I'm trying to do, you understand in Weber electrodynamics is not good for speeds close to the speed of light. What I'd like to be able to do is from Weber field approach, be able to derive this equation, this E, the electric field. This equation I understood came from the special theory of relativity. That's how I learned this equation originally in graduate classes. They say, well, now we're going to go into the special theory of relativity with Maxwell's equations, the transformation equation, blah, blah, and you can come up with this equation, which has been verified by experimentation. And I'd like to do that for Weber. Haven't done it yet. On the other hand, I really don't want to introduce special theory of relativity into Weber if I can avoid it. Well, I've looked at Bill Lucas's approach, and in his book, The Universal Force, Volume 1, he presents 6 empirical laws of electrodynamics, and from these, he's able to derive this equation for E, the electric dynamic field. And he does that, if I understood it correctly, without introducing the special theory of relativity. However, this requires the 6 empirical laws versus Weber's 1 potential energy function. So it would be nice if there was some way to reduce those 6 empirical laws into 1 equation, 1 assumption, 1 something. So I'm still looking. But in my recent reading, I find that this equation has nothing to do with the special theory of relativity. That was a mistake on my part, because I was taught that equation through the special theory of relativity. But Oliver Heaviside, and yes, that's the guy who edited Maxwell's equations, derived and published this back in 1888. That's 17 years before the special theory of relativity was published. So as Bill has derived, and now further in my reading, Heaviside has derived this equation from Maxwell's equations without using all the assumptions of the special theory of relativity, because that special theory of relativity was not around in 1888. So I've been reading recently Jefimenko's work, particularly his book Causality, Electromagnetic Induction, Gravity, and some others. And he points out another issue with Maxwell's equations in that they are not causal equations. You can have a cause precede an effect, which is weird. It's like going backwards in time, time traveling wave functions and so forth. So Jefimenko introduces his retarded time and fields and scalar vector potentials. It's a lot of what Jefimenko's work is about, is introducing time retardation into classical electrodynamics, because he's correcting this causal problem with Maxwell's equations. And when he does that, he too can derive this equation, again, without the special theory of relativity. So I highly recommend Jefimenko's books, which I'm trying to go through. I'm showing 3 here: Causality, Electromagnetic Induction and Gravity, Electromagnetic Retardation and the Theory of Relativity, Gravitation and Co-gravitation. These are excellent books, and I don't know, I tried to read his books years ago, and I just got lost. I wasn't ready for them yet, but after studying a lot more of Weber electrodynamics, I seem to be ready for them now, and they're just brilliant books. So
what does he think that gravity is then? Since that's always this thing about, well, what's the relationship between gravity and electrodynamics?
getting there. Further on, in a recent paper, recent being 2007, Heras, I believe that's how he pronounced his name, I don't know, Heras published a paper, Can Maxwell's Equations Be Obtained from the Continuity Equation, in which he showed that with a couple of assumptions. Assumption one, conservation of blank. Fill in your blank. Conservation of charge, conservation of mass, conservation of you name it. If conservation of blank holds and can be expressed with the equation the divergence of J plus the time derivative of rho is equal to 0, which in electrodynamics is the continuity equation, where J is blank in motion, whatever your blank is, density function, and rho is the blank density function. And with assumption 2, J and rho, whatever those are, do not extend to infinity. If you have that kind of conservation of something and time retardation, as in Jefimenko, then you can get the 4 generalized Maxwell's equations. They're just derived. They come from the continuity equation and retardation of the fields. So in Heras's paper, he derives these generalized Maxwell's equations. Okay, and alpha, gamma, beta, these are coefficients to be determined. C squared is a velocity, not necessarily the velocity of light, particularly if you're not talking about electrodynamics. It's a speed of wave propagation. So in particular,
Was the magnetic field in there anywhere?
Yes.
Because I
Here we
didn't see
go.
like any B's or H's or...
Right, because this is generalized. This could be for hydrodynamics. This could be for gravity. This could be, yes, for electrodynamics. And in electrodynamics, this equation is the continuity equation. J is the current density function. Rho is the charge density function. And the alpha, beta, gammas are here for SI units. F is really the electric field, electrodynamic field. G is really the magnetic field. And you have Maxwell's equations. And because this is derived using the Jefimenko time-retarded fields and potentials, you also get that electrodynamic function. All of that from just these 2 assumptions, that you have a conservation of something that can be expressed with this equation, the continuity equation, and these things do not extend to infinity. You get everything. To me, that's a big wow in my learning of electrodynamics in particular, but also of gravity or any other subject, provided you have a conservation of something with this continuity equation. So can you use this approach? You can use this approach with gravity. You would then have conservation of mass or mass energy, possibly use it with with hydrodynamics, potentially conservation of vortex number. The reason why I say that is because I just found a very interesting book by Hills called Gravito, Electromagnetism, and Mass Induction, where he summarizes practically everything I've already presented, but then applies it to gravity, cosmology, etc. From the back of the book, I'll read it here, the back of the book, the description of the book, starting from the single postulate of the conservation of mass energy, it is shown how gravity can be reformulated as a set of generalized electromagnetic type field equations. This unconventional approach leads to some remarkable new phenomena including mass induction, superconductors as laboratory gravity sources, and longitudinal gravity waves. On the cosmological scale, it removes event horizons and black holes and is found to provide the natural theoretical framework for pseudostatic cosmology. And so in that book, he's applying what I've presented before based on that Heras paper and Jefimenko's retardation of fields and potentials. He is also able to implement, that is, put into the math, a derivation of Mach's principle of inertia. So inertia is the result of all the other mass in the universe. Mach did not write that mathematically. He just kind of stated that as a possibility. But Hills is able to derive that in his book, and he applies this to hydrodynamics, to cosmology, to plasma, speculating that it could replace what we currently use in magnetohydrodynamics and other topics. Very interesting book, highly recommend it. Only partway through it, but thought I'd let you folks know about it and this whole research program that I'm doing. And that's it.
So going back to your previous slide there, he cites all these interesting phenomenon, but have any of those phenomenon actually been shown to actually exist? I mean, what would be mass induction? That doesn't even make any sense to me.
Yeah, well, I'm not that far in the book yet.
It's like, well, you can cite all kinds of phenomenon, like ghosts and Sasquatches, but if they don't exist, then that's just sort of proving the point that you've gone down the wrong path.
Read the book, make up your own mind.
Yeah, I guess.
I'm just pointing it out that to me this is absolutely astonishing that from very simple assumptions, an assumption involving the conservation of something, that you can derive generalized Maxwell's equations to apply to that whatever conservation thing is.
Now, I don't know what you mean by generalized Maxwell's equations. I mean, that
I'm showing it.
Doesn't make any sense to me.
I'm showing it here.
There. Yes, that's what you have there, but that.
But see this equation, the continuity equation. I don't know what J is, and I don't know what rho is. Okay, but it's whatever that thing is, blank in motion. Okay, and a blank density function. If you have this equation with time retardation, you can derive all of these equations.
And what do these G's and F's and B's?
Whatever your thing is, for example, electrodynamics, F would be the electric field, and G would be the magnetic field. But if you're not in electrodynamics, say it's gravity, well then this F may be the gravity field, and the G would be a co-gravitational field of Jefimenko. You get these equations, all of these equations, only because of this equation in time retardation. And yes, we may not have measured co-gravity yet, but these equations would still hold for gravity. So anyway,
no, I that's just
the
throwing red flags all over the place.
The equations hold, whether it's physically realizable or physically measured. Yes, that's another question. But these equations hold regardless of whether it's electrodynamics, gravity, or any other topic, hydrodynamics, as long as you have this equation, the continuity equation, for that particular topic.
Now you're saying the generalized equations can be derived from that?
Yes.
And I don't know. I'm having a hard time seeing that. It's more like you took Maxwell's equations and generalized them and got back to the original assumption or something like that. But
this is
but I guess
Heras
there's a
Paper.
derivation there, right?
Yep, Jose Heras. And if you want to go through the math, here's all the math. I have gone through the math this week to verify it and to learn it. And it's math on math on math. And yes, you do come up with those 4 equations. And in electrodynamics, it's just Maxwell's equations.
All right. So, Bill, this seems like right down your alley. What do you think?
Excuse me. In the work that I have done and following Maxwell, there's 6 Maxwell's equations, not 4. There's Lenz's law and Lorentz's law, and they are not included in this work. The second thing is when you derive the force of gravity from this approach, are you able to describe the gravity in our solar system and in spiral galaxies without having to invent dark matter and dark energy?
Well, as far as I know, haven't gotten to that part of the book yet, but I'm going to tentatively say yes. But I haven't studied Hill's book enough yet to know for sure.
A second question is, can you explain the origin of quantum mechanics from this approach? In my approach, the origin of quantum mechanics is due to the building block of all electromagnetic material being made from solitons. And solitons have standing waves in them, and the standing waves give rise to all the quantum laws. And so you can derive the quantum law for the atom, and you can do it for the solar system, and you can describe the orbits of the solar system and that sort of thing. So I guess the question is, how complete is work? Because it should be able to describe all these things.
Right.
But in the work that I have done, gravity is an electromagnetic force between vibrating neutral electric multipoles, dipoles, quadrupoles, octopoles, etc. And that turns out whenever you have a vibrating multipole, it has to radiate energy continuously. And that is what we see when we look out into space. We call it the cosmic background radiation. And you can actually predict the spectrum of that radiation directly from electrodynamics of multipoles. And so that's something that needs to be explained. And the fact that the NIST data shows that there is no longer any strong interaction or weak interaction forces in atomic nuclei, and you don't need to have a strong interaction force and weak interaction force in your theory of elementary particles. This means that there's only one force in nature, the electromagnetic. And so if you have a solution that works for the electromagnetic force, it will kind of be able to work in these other areas because electrodynamics is able to work in these other areas when it's complete.
Interesting.
So, James, you had a question about assumption number 2.
Yes,
Yeah, totally.
just if Bill could comment why that assumption is necessary. Bob Gray.
Well, assumption number 2 is that the things do not extend to infinity. I'm not sure that I would put that down if I was to do this as an assumption, because I don't know of anything that extends to infinity. So I wouldn't even take it as an assumption, but the math requires it because they do in the vector calculus, you're doing integration over all space. And if these things extend to infinity, then you cannot change the integration over all space to a surface integral and have that surface integral go to 0. Because you usually take the surface to be out at infinity, where this J or rho or whatever these items are do not extend to infinity, so J and rho would be 0 at infinity. So the surface integral at infinity would be 0. You can't do that if J or rho extends out to infinity, and so the math wouldn't work out right. So they're doing it simply so they can change volume integrals into surface integrals and have that go to 0. But I wouldn't take that as an assumption. I don't know of anything, a current. Show me a current that really extends, to infinity. I don't even know if infinity extent would really make physical sense.
Well, to me, this tells me that this is just a sign that this continuous space-time theory math that's being used without full quantization is limited. It has defects. Two of your equations show differentiation with respect to time. What if time is quantized? So there is no such thing as an infinitesimal increment in time.
Right.
Anyway, that's my thank you for your explanation.
Yeah. Sure.
Another comment on that is William Hooper at University of California at Berkeley did experiments where he measured the tensile strength of the electromagnetic field. And what he found is that it is the strongest thing in the universe, and you can't cut it off or chop it into pieces. And so even when you have something like a toroidal ring or a soliton, that's the building block of all elementary particles, even though we like to talk about it as a toroidal ring of charge, it turns out that's an approximation, because the field is continuous up to and beyond the soliton, and so that indicates that it may extend to infinity. We just don't know how far it goes, or it may curve around and come back. But
so how do you test the tensile strength of the electromagnetic field? Because typically tensile strength, you take like a bar and you lock it between two things and then you stretch it until it breaks. That's how you test tensile strength. So how do you test tensile strength? It's something you can't even grab hold of.
William Hooper published a book, and in that book he describes how you measure 13 properties of the 3 types of electric field and the 3 types of magnetic field, and they are all different. No two of the fields have the same properties.
Well, that doesn't tell me anything about how you can say that the electromagnetic field even has a tensile strength.
Well, if you read his book, you can see all the experiments he performed at University of California.
Well, I'm not going to read his book, so I was just kind of seeing whether you had any idea how that's done.
Oh, I have read it. Yeah, I can't tell you right off the top of my head. I'd have to go back and look.
Because that's just one of those things where I go, well, how on earth do you do that? And sometimes we just accept that. Sometimes we read a book and go, oh, yeah, he explained that. But then we don't actually remember what the key point there was.
One of the properties that he measured is whether or not that type of field can be shielded, because the force of gravity cannot be shielded. And if gravity is electromagnetic, then it has to be due to certain properties of electromagnetic fields that can't be shielded. And it turns out that more than one type of electromagnetic field cannot be shielded, but the others can. And so they ignore these experiments in the typical textbooks today because it doesn't meet their desire for a particular theory. They want, like in politics, there's politics and science, and they want theories that do certain things. And we've never discussed this, I don't believe, on this show, but when our nation was founded, Thomas Jefferson and James Madison were intimately involved because there were what we call revivals going up. The first and second great spiritual awakening was occurring in America. And in this revival, there were three parties. There were the party in support of the established church, the parties responding to the revivals in the new churches like the Presbyterian, the Methodist, and the Baptist churches, and then the people who didn't care for religion at all. And so they introduced into the Constitution and the Bill of Rights the concept of a wall of separation between the church and the state. And it turns out that the people who were not in favor of any religion of any sort, they figured out how to use the government and science to combat religion. And so all the theories in modern science since about 1850 are false. They use assumptions that are false, and they changed the scientific method in the 1850s to what we call the empirical scientific method, which took the role of logic out of science. You had to predict experiments, but your assumptions did not have to satisfy logic. And then,
say, Bill.
Yeah.
Can I ask you a question, sir?
Sure.
Your mention of shielding came a very simple experiment came to mind. What if I'm weighing an object, like say a silver coin or anything, and I put it in a Faraday cage? Okay, would the weight be then less because it is shielded electromagnetically? I proposed this experiment really in the form of a question to get more elaboration from you as to what you really meant by shielding or not shielding.
The Faraday cage can only shield some of the 6 forms of electric and magnetic field. There's three types of electric field, 3 types of magnetic field, and only some of those fields can be shielded by the Faraday cage. But we have refused to acknowledge that when this was measured by William Hooper. And it wasn't done at a place that's backward. It was done at University of California at Berkeley. It was a well-known institution where they do a lot of good work. And so anyway, he measured that, and he showed that there are forms of the electric field and magnetic field that cannot be shielded. And when you say that the gravitation is due to the vibration of neutral electric multipoles, you're using that field because the other fields all average out to 0. But those fields that cannot be shielded, they do not average to 0, and you're able to predict the value of G.
Well, let's go back to square. Let's go back. Excuse me for interrupting, but let's go back to square one because I find this fascinating. This is news to me that there's three or whatever number of types of electromagnetic fields. What is the reference or source on this so I could become better informed? Because everybody else is talking about, not here, but I mean in conventional physics, is talking about the electromagnetic force and field and so forth as one force. So what is this 3 different types now?
Okay. One type is just the regular field. The second type is the
regular
E field. The second type is the cross product of the field, and the third type is the time dependence of the field. So you've got 3 types of electric and 3 types of magnetic field: the time dependent, the cross product, which we put R cross E or R cross something, to represent that field, but it is a unique field. It has different properties, and it's just not a mathematical term you're putting in that can be declared a new type of field. So that's what Hooper did. And
Bill, if I go to the lab and I've got my wires and electronic equipment and so forth, which I have incidentally, how could I set up each of these 3 different fields?
He describes it in his book. Let me see if I look in my book, I can find the reference to it. Let me take a look and see what I can
This is
find.
James?
William Hooper. You can search
James?
on William Hooper, and you can see there's like motional electric field. Well, I was kind of curious
Okay.
about this cross product field. Like, what would be the cross product of the electric
Okay.
field, right? That's,
Hold on, James, maybe this may not be the way to interpret Hooper's work, but the way I look at it is you have the electrostatic field, that's one. Then you have a term which is the time derivative of the vector potential, that's two. And then you have a velocity cross magnetic induction, that's three. All of those are in the force equation. And so those are the three separate, quote unquote, electric fields.
Yeah, that you're right. I think you're
Okay.
better on that than I did.
See, there's
If I
three
could make
different
a
forms of
couple of
electric
comments,
fields.
just on the presentation, just maybe 2 or 3 points, Franklin. First of all, perhaps surprisingly, I'm not at all surprised at the results that Bob has indicated, because I've actually rather suspected this for some time. I haven't in all cases worked out all the details, but because of the analogies in nature which exist between the various forces, and I suppose Bill has been adverting to them in another sense, but continuity equations and conservation equations and so on, it's not surprising that you would get similar equations, and hence the generalized Maxwell's equations as you call them. But just a couple of points. First of all, when you came to retarded values, retarded potentials, and so on, my ears popped up a bit there, because conventionally, say in electromagnetism, when they use retarded values, they use the actual speed of light. So the time difference would be something like r over c, where r is the distance of separation. Now, I'm concerned because it appears from experimental evidence and theories built thereon that for other forces, well, for electrostatic fields or for gravitational fields, or even, I maintain anyway, we've discussed this before, I think, for the transmission of electric current, the speed would not be the speed of light. It would be a speed very, very much more, orders of magnitude more. So I'm wondering how that can be taken into account in the retarded potentials. And one other point was that, as I say, I was not surprised at the results, but you derived the Maxwell equations, basically. And yet, Bob, that might have been slightly in contradiction to what you started with, because you said, Maxwell's equations are not complete. One needs to go to Weber electrodynamics. And, so you didn't get these R terms, R1, R2, R3, I think, in the generalized equations. And I think, we've discussed this again previously, and maybe we came to the conclusion that the only way to discriminate between Maxwell's equations and the Weber equations would be experimentally, and we perhaps don't have enough experimental evidence to discriminate between them.
That's exactly where my research is going, not so much the experimental, but the theoretical. So I started with Weber, and I'd love to get that equation for the electric field involving what I thought was a special theory relativity equation that's verified in all these experiments from Weber electrodynamics, and I cannot do it at the moment. And when I try to derive, set that aside and just derive or compare Weber electrodynamics to Maxwell's electrodynamics, I'm finding that Maxwell's electrodynamics comes up short. There's some problems with Maxwell's electrodynamics, and I'm trying to chase all of that down as well. Then I'm trying to adapt what I presented today to Weber electrodynamics, the time retardation and everything. Can I adapt that to Weber electrodynamics so that I then do get that equation for the electric field that seems to be valid from experimentation. That's the theoretical mathematical aspect that I'm really trying to focus my time on, because something is a little bit off someplace. I'm just trying to nail that down and correct it. And I'm not sure what it is yet.
There is a way to do that, and it comes from Isaac Newton. And Isaac Newton said, in each field, like electrodynamics, you perform as many experiments as you can think of and develop empirical laws. And then you take the complete set of those empirical laws, see how many unknowns you have, and see if you can solve them simultaneously. If you take the 6 equations, Maxwell's equations is 6, including Lenz's law and Lorentz's law, and you solve them simultaneously, you don't need the theory of quantum mechanics, and you don't need the theory of special and general relativity. You get everything that those theories can produce, but without their bad assumptions, just from the empirical laws of electrodynamics. And in those empirical laws, there's 6 empirical laws, but there are 8 unknowns. And two of the unknowns are the prime and unprime coordinates and the prime and unprime time. And you get those from Galileo's Galileo transformation, not special relativity. And it's interesting that you get the same total result that special relativity would give if you combined it with electrodynamics, but you don't have to combine it because the information that you need is in Lenz's law and Lorentz's law. And so that's what I think is the significant thing that we need to notice. And also, when Oliver Heaviside modified Maxwell's equations, he had to solve the problem. He had 8 unknowns. And he did it by coming up with reasons to discard some of the terms, and he did it by ignoring certain effects that he couldn't get rid of. And so you don't have any of those problems if you take the full set and use the Galilean transformation to get between the prime and unprime coordinates. And so anyway, that's what I think is the significant thing we need to notice. And until you have tried doing that yourself, you don't know how well it works out. And what you find when you do the solution is you discover that in electrodynamics, the fundamental quantity is a soliton or a toroidal ring, and it comes directly out of the equations of electrodynamics. And so that is, and we've been able to, Nobel Prize winner Arthur Compton and his last graduate student Winston Bostic, they have discovered that. They did all kinds of experiments with it. They've been reproduced around the world, and it's ignored by the politically correct scientific establishment because there's religious connotations to this if they let it be. And they know that, and they don't want that connotation. They don't want the idea that the source of all electric fields and magnetic fields is God. And when he disturbs that, he makes solitons, and from the solitons we make elementary particles and atoms and nuclei and molecules and all the matter in the universe. And so that's where the problem is. It has to do with the first and second great spiritual awakening and people who are in rebellion against that. And they, according to the education framework, you are not allowed to say that in any school that receives public or government funds. And that's all your religious colleges but 2, and all of your state and private colleges. So there's only 2 colleges in the United States that could tell you that, but they don't want to get all the problems with it. I've talked to the chairman of those departments, and they, or the president, and they don't want to get involved with that because they feel like they'll be shut down. And so anyway, that's kind of where
Bob,
we're going. And
Bob did mention something about special relativity and how that the equations he came up with actually are not they were invented like 17 years before special relativity was even mentioned. And so my question is, and this is something I've never really fully understood, which is what exactly is special relativity? It's kind of like when you talk about quantum mechanics, it could almost be anything. There is this, one equation, 1 minus v squared over c squared, which appears in his equations, but is that special relativity itself? What do you think special relativity has to do with anything, or is it particularly what is it actually saying?
Well, the problem with special relativity is you don't need it. It comes directly from the equations of electrodynamics. The second problem is all of the fundamental assumptions of special relativity are known by experiment to be false. But
you got those 2 postulates, and they're both wrong, but experimentally.
Yeah, and so what they did is they, instead of falsifying the theory, they changed the scientific method so that you don't falsify a theory because its assumptions are false. You only
I don't know that they actually derived anything that interesting.
Experimental data.
Because here I'm looking like at the wiki definition of special relativity, and the surprising thing you see about it is that it's all words. It's not really actually. There's nothing there that's actually testable. See, they say that it is a physical theory regarding the relationship between space and time. Okay, I'd love a physical theory regarding the relationship between space and time. But reading this thing here, they say nothing about what space is. They say nothing about what time is. So how could that possibly be an explanation or being a physical theory of what space and time is? I mean, a physical theory of what space and time would be like saying time is a quantized thing that we could measure that happens through the universe, and we could call that time. That's, for example, like in the theory that the world is a computer, that there's a particular time slice, and that's when things happen. And then a physical explanation of space might be that it's made out of these particles, and that would be like a space and a time theory. When I look at special relativity, I just don't see anything. I don't see any explanation. All I see are these 2 postulates that the laws of physics are invariant and that the speed of light in a vacuum is the same. Those are the only 2 things I see, right? And as Bill says, both of these can be probably shown false experimentally, right? So once again, that's why I have this question on, what the heck is special relativity? It doesn't seem to really explain anything. We do have these dilation formulas for like the time and things like that, but once again, those equations relied on that 1 minus v squared over c squared thing, which existed well before special relativity. So Bill, what is it? Is it just a big lie? What?
This article you're seeing on the internet does not talk about the assumptions of special or general relativity.
Well, it does. That's the first 2 things that got up there.
Not assumptions.
See, those are the 2 postulates. See, the laws of physics are invariant, identical in all inertial frames of reference. And 2, the speed of light in vacuum is the same for all observers, regardless of the notion of the light source or observer.
Those are conclusions from the theory. It's not the assumptions of the theory.
No, those are not the assumptions of the theory? Well, I've always disagreed with these two postulates, because if you read the actual original paper, in no way, shape, or form are they saying that the speed of light is the same for all observers, regardless of the motion of light source or observer. That's just not what Einstein said in any way, shape, or form.
Yes, he only says that it's independent of the motion of the source. But later on in the paper, because of the complete reciprocity of the whole system.
And he certainly didn't say the speed of light in vacuum is the same for all observers. I mean, that definitely, if you start talking about the observers, then that's definitely not true.
That's misquoted. That's true. That's misquoted.
Yeah, that's just totally misquoted. I mean, I think what Einstein said was perfectly correct, which is that the speed of light measured to, I guess, any inertial frame of reference is going to be the same. Of course, but they're saying weird things like the observer could be moving in some non-inertial way, and that or that there could be two frames of references moving relative to each other, and that the speed of light would be measured the same even between those two inertial frames of reference. But Einstein never said anything like that. What Einstein is more saying is, like, if you are sitting in a room and you have a speaker on one end and you measure the speed of sound going through the room, the speed of sound does not depend on the motion of the speaker, or the speed of sound does not mirror the motion of the receiver. The actual physical motion through the room is going to be the same speed, right? And that's intuitively obvious if you think of it like being like a sound wave, and that the sound wave moves relative to the medium, which is generally considered stationary.
So therefore, the second postulate, as it was quoted in the 1905 paper, is trivial. It's obvious.
It's trivial.
That's true. But I think if you drill down further into the consequences of what he's doing, with complete sort of reciprocity of frames and so on, you would probably deduce actually that the speed of light is independent of the speed of the observer, which is actually a nonsense. But that does follow from not from the postulate. It is misquoted there, and of course the gamma factor, 1 minus v squared over c squared, and with the sine term in the denominator of the equation shown earlier. I mean, that originally came from Lorentz. And I suppose what the special theory of relativity is doing is Lorentz was looking at the theory of the electron and looking at electromagnetic theory. And Einstein was just saying, oh, those equations apply to everything, to simple dynamics.
I still don't know what he was trying to say. I mean, to me, it's like I don't even know when people talk about special relativity. It's like, well, what the heck are you talking about, right? Are you just talking about his paper? Are you talking about the two postulates? Are you talking about the time dilation theory? Are you talking about E equals mc squared? It's just, this is the first problem with special relativity, and that's like he's not really saying anything, right? And it's like all the mathematical equations that are in that paper, Lorentz came up with them, a long time before he did, right? So what's the big deal here?
Well, it's a bit like a religion or a philosophical doctrine or something. It's postulated, and one cannot disprove it, because by definition it's accepted as dogma by the orthodox scientists in this case.
Well, I don't even know what you could accept here as dogma. It's like there's some assumptions, and that's not dogma. That's just assumptions, right? That's not really by itself proving anything. And then he has his equations, which are Lorentz's equations. So let's see here. Kurt has got some maybe some comments here. So let's see here. Now we are up to our maximum of 6 people allowed in the live room. So if you just want to listen, then please go to our one of these two. Let's see here. Did that not show? Go to one of those two links in our YouTube or Facebook, and so that you don't take up a slot for someone who needs to speak. Because if you're in the live room, I'm going to expect that you want to talk, and I will put you up. But I can only have 6 people up at any given time here. So I'm going to say take off Alistair, and then Kurt just disappeared. Darn. Okay, I was going to have him speak. Okay. But we do have Michael here, and Michael, can you hear us? You do have your mic open, so I would presume that if you're in the live room and you have your mic open, that if I see that, I'll presume that you would like to say something, and I will put you on the screen. Is how it should work. But it sounds like Michael is shy, so we'll put him back down there. But I want to ask Ian. So, I mean, one of the strange things, I guess, that Bob was bringing up is that he has these generalized equations, and you could generalize them to gravity. And so you could have like the equivalent of the, so you have the electric and the magnetic field, and then you could have the gravitational field, and then like the equivalent of the magnetic field to satisfy these equations. Now that seems a little bit, I don't know, crazy to me. To me, the gravity equation is easily satisfied with the standard gravitational equation, a product of the constant g times the masses over the radius. What's wrong with that? So what did you think of that whole concept that you could extend the Maxwell's equations to, say, gravity?
Well, it could be stretching the point a little, Franklin, but I mean, the force of gravity can be made analogous to the electric field, the force due to the electric field. Now, I think he talks about the analogy of the magnetic field as being co-gravity. I think that was the term used.
Yeah, co-gravity. Is there such a thing as a co-gravity? I don't think so.
Well, maybe Bob would be the better man to defend us because he's been reading the various things. It's a little tentative, and I am skeptical. I think you're right to be skeptical about it. But I mean, the similarity of the basic equations, of the continuity, of the conservation, of the potential, of the sort of Laplacian type or Poisson type equations would lead one to indicate that there probably is an underlying similarity between them, and maybe we haven't sufficiently studied these co-gravitational effects, whatever they may be.
No, I don't know about not sufficiently studied. I think they just absolutely. I think we would have noticed it by now. It's like we notice the say magnetic effects very much from electric effects. They're pretty obvious, right? They both cause attractive forces to appear and in different directions and such like that. And I think that if there was a co-gravity force acting at like cross product to the regular gravitational field, which is what Bob seemed to be indicating, or at least, this work that he was looking at seemed to be indicating.
I think some of the work maybe of David Tome or something, people like that, would indicate that when you get into these so-called fictitious forces like centrifugal forces and Coriolis forces and so on, they would be basically the cross product of the velocity and the force, perhaps. So, or the acceleration. So that would be the nearest, I think, that one might postulate at the present state of knowledge.
Okay, let's see. So Bob has gone into listen mode in YouTube, but Bill has requested that you send a copy of that PowerPoint presentation to him with the work of Jefimenko and Heras and Hills. So he would like to have more information on that particular slide deck there. So Bill, if you could send that to him, I think that would be great. So let's see, who else do we have in the line? We do have Alistair. So I don't know if Alistair, you wanted to say anything about this whole topic of Maxwell's equations or generalizing them?
I'm not so much of a symbolic math kind of guy. Like if I hear a math term and can
Question.
see a picture of it, I'll understand it, but I don't know the language. What I did want to comment on
So,
earlier, somebody had mentioned about assumptions, and the assumption I like to question is, how can anything exist that doesn't have a physical form? So we talk about fields, we talk about waves and energy, and these are non-physical things. How do those get justified as the way of accomplishing as the way something can work?
Well, I would say that, for example, like the magnetic field, that's like a non-thing, right? As far as we know. But we see its effect on things, right? Like pieces of iron, right? We take the magnet, which is emanating theoretically the magnetic field, even though it's basically a non-entity, right?
I'm not questioning the observation that there are effects that appear to be like forces and mediumless waves and uncontained energy. But when we're talking about the nature of existence, how do we not recognize that those should be absolute last ditch inclusions in a theory instead of looking for a theory that doesn't need those, is purely physical mechanical?
Oh, well, I would agree with you there. I mean, that's part of the thing that what we dissidents do, and that we don't like things like just saying, oh, the magnetic field is there, it just works this way. I think we would much rather say that, or at least I would rather say that we need a physical theory to really explain that, because the magnetic field can't truly be nothing, because nothing couldn't pick up or keep our refrigerator magnet on our refrigerator if it was nothing. Physically, there must be something there. I prefer to think that. Which is why I make my space universe, whatever, and I think you as well. We fill it with stuff, right? We fill it with actual physical stuff. And then once we fill the space with physical stuff, then there is indeed a connection, a true physical connection between the magnet and the piece of iron it's attracting, right? There's not empty space. There's something in there that's actually physical. And the only reason why this can get to that is because it's going through the chain of material that's between those two things.
Because somebody mentioned that the scientific method is you make up a hypothesis and a prediction, and if your prediction is correct, then your hypothesis, the concept upon which your prediction was built, is assumed to be correct. So toss in an extra dimension, make a prediction. Prediction's accurate. Oh, there must be an extra dimension. What the hell is an extra dimension? What is a force? What's an uncontained energy? What's a wave that is in nothingness? These are all assumptions I'm not okay with. If we're going to talk about assumptions and the scientific method, and that the assumptions should have a logical basis, then we have to go back to the ground floor and look for a theory that does not include any illogical assumptions.
Yeah, I mean, a basic illogical assumption would be like if mainstream presumes that vacuum has really got nothing in it, but yet we observe electromagnetic wave phenomena. Now, really, I mean, it seems pretty clear it's a wave. If you have a radio receiver and you hook it up to an oscilloscope, you can see something
Again,
that looks very much like a wave, right?
not questioning the existence of waves. We
Well,
know
I'm just saying that the
we see
logic
waves
is
in water.
illogical.
We see waves in air. We see waves all over the damn place. Waves exist, but that's because they're a product, not the cause.
Yeah, I'm just saying it's illogical for us, for mainstream, to presume that there is no medium in space. That is clearly, I would say, illogical, right? That's abandoning the role of logic in science. If we were to use logic, we would see that, I see a wave, and waves get from place to place by traveling through a medium. Therefore, the logical conclusion would be, if we were using logic, that the vacuum of space must contain a medium, right? Rather than nothing.
Sure makes sense to me.
But I think, though, that is kind of the exact assumption that Bill Lucas is making, which is he just presumes that the electromagnetic field is itself a primitive. But so I'm challenging you, Bill, on your own saying. You're always saying that we're abandoning logic in science, and I'm saying that you have yourself abandoned the simple logic that if we see a wave, that then there must be a physical medium. But you would deny there's a physical medium. So I think you've abandoned the role of logic.
We do experiments to find out what is the case. That's why we, following Isaac Newton, we try to develop the empirical laws that are relevant in each field. So we have empirical laws for gravity, we have empirical laws for electric and magnetic fields that we can measure in the laboratory. And then once you have that, you have to try to put that together if you want to find a universal force or something that's more fundamental.
Well, that's not really what I'm talking about. I'm talking about specifically, I just put up this specific challenge, since we're talking about science and logic, right? So, would you agree? First of all, let's get what your actual viewpoint is. And so the viewpoint I'm trying to find out whether you believe or not is whether space contains some sort of medium, like air, right? So either you can believe that, space does contain some kind. Now, you can disagree what kind of medium it is. It could be anything. I prefer to think of it as like a field of positrons or electrons. Alistair may think it's his balls. Anybody can feel free to say whatever the heck that is.
That's
But
right.
that's one specific view. Now, I don't believe that you believe that is the true view or not. I mean, would you agree or disagree with this hypothesis that we're looking at?
William Hooper did the
something.
experiments to determine what is in space. And what he found is the electric and magnetic field is there everywhere, and it has tensile strength, and it's the tensile strength that enables forces to occur.
Yeah, but that doesn't say anything about what space is made out of. I mean, that's all properties of space.
It's only made of the field.
No, that's not saying what it's made out of. All you've said is that when we measure space, we can see the magnetic field and we can see the electric field, and it's
Right.
everywhere. Now,
But
I would totally agree with that.
Winston Bostick and Arthur Compton did the experiments to show that the building block of all matter, all elementary particles, everything, is the soliton. And the soliton is composed entirely of the field. And so
Yeah, but that's still not saying
there
getting
isn't
down to the
anything else
basic.
but the field and the solitons in the
But we're
universe.
not talking about particles. We're talking about, vacuum space, okay? Go take the most perfect vacuum you can find in the universe, and then what is that made out of?
It has
Now-
electric fields everywhere.
Yes,
And
it does
magnetic
have electric fields, but you haven't said what it's made out of. The electric field is a property of space. It's not space itself, right?
Well, it depends on a lot of things. If you are religious, you say the source of the electric and magnetic fields is God, and there isn't anything else. If you're not religious, you want some other physical explanation for so you want things like charge and stuff like that to be the source of the electric and magnetic fields, charge and current. And but what Arthur Compton and Winston Bostick discovered is the concept of charge is an approximation to the way the field is distributed when you have a structure in it. Like,
yeah, but Bill, I'm trying to trap you here. So just so you understand what I'm trying to do, because I'm trying to keep you on topic, right? I'm trying to trap you into this specific question, because what we're talking about here is whether we're using the role of logic in science properly. Okay, that's the actual topic here. Are we using the role of logic properly? And to test that, we're using this one specific instance of how do we count for wave phenomenon through vacuum, right? So the argument here, and the thing that I'm trying to specifically get to, is that if we observe wave phenomenon, electromagnetic wave phenomenon, then is it logical then to conclude that space must contain a medium? Right now, mainstream, and I'm thinking you as well, would deny that there is any actual medium, that there's no physical medium required, right? You would say something like, there is no physical medium, that's God who allows that to happen. And so if that can happen without any physical medium.
Yeah, see, the Bible says that God is the creator of all matter, and he brings stability and control to the universe. So the only way he can do that is if he has some way of controlling everything. And the electric and magnetic field gives him that opportunity. And now that we have discovered that we can make all elementary particles out of solitons, we can do a theory of elementary particles that's better than the politically correct theory, we have made great progress in science. And we don't have four forces, we only have one.
Here's the other problem that I would like to challenge you for, as far as are we following are we using logic in science, which is, if you believe that everything is made out of the soliton, then why hasn't mainstream found it? I mean, and I think they would have found it. They've got particle
accelerators. The scientific community has found it and verified it, but the political community doesn't like that solution.
Well, I suppose that's always a possibility, that they have actually found it, but we will never find the soliton in any of our physics books, of course. But once again, that might be because
go to the
totally
internet.
surprised.
You'll see solitons in all kinds of fields. You'll find it in fluid dynamics. You'll find it in smoke rings and all kinds of things. Sure, you
can find solitons in smoke rings,
where they make solitons.
All that says is that kind of shape can exist, but it doesn't say that particles are made out of those things. In no way does the existence of smoke rings say that an electron is made out of solitons. There's just no connection there at all.
I really want to jump in for a second, because
Sure.
you guys kind of started back and forth based on what I said. I just wanted to be really clear. I wasn't pointing a finger at nobody specific or calling anybody illogical or anything like that. I was just grabbing onto the fact that somebody, I think it was Bob, had said that we make illogical assumptions, and then if we find some confirmation for that illogical assumption, we go, well, the illogical assumption must be correct. And I don't find that satisfying, but I didn't mean to, it was Bill, sorry. I didn't mean to say that this theory or that theory or the other theory is not logical. I wasn't being specific with my lack of satisfaction of the lack of logic.
Yeah, that's why I tried to get things more specific and personal, because I think we do kind of speak in generalities, but ultimately, one of the criticisms with our dissident group is that everything's accepted, and there's no way to tell the difference between what is logical and what is not, because we really don't put any rules. We really don't, sit there and try and do what I just tried, which is try and pin someone down into saying that what he's thinking does not follow the rules of logic, right? Or at least trying to understand where his logic comes into. Because if you are willing to accept things like, God is responsible for the electromagnetic field, then at that point it does indeed become logical that you can have a wave through a non-medium because God is in charge of the medium, right? But other people may not accept that. They may say, well, maybe I think I have better explanations. And then it becomes a contest between who has the better explanation. So, in contrast, though, I wouldn't say that God is in charge of the electromagnetic field. I would say that God has got other things to do other than worry about the electromagnetic field. If I were God, I would set up a system that just automatically takes care of itself. So if I were God, I would invent the electron and I would invent the positron. And don't ask me what those two things are. But we do know those two things exist. I mean, from a mainstream perspective, definitely the mainstream would say, yes, the electron and the positron would exist. We can see that in the physics textbooks versus, say, the soliton. Now, the soliton could exist, and it could be just totally suppressed, like Bill says, or it just might not exist versus the electron and the positron, which have been positively confirmed to exist. And I think everyone would probably agree they exist. So from that standpoint, if your theory relies on electrons and positrons and protons and neutrons and things that we do know exist, that has a leg up on the theory that says that solitons make up everything, which at least right now, the mainstream would disagree exists. So, and then you have to balance out things. It's like, do I believe in a theory that has solitons? Because if I do, then Bill says it can predict all these properties and things like that. Versus, or if you have the one that says electrons and positrons, it's like, well, that's at least based on things that we know about, but I can't predict quite so many things, or at least no one's helped me out to make that happen. You got to balance these things out, I suppose.
A physical field can explain a non-physical phenomenon, or a seemingly non-physical phenomenon. But how does a field, if there's supposedly no underlying physical mechanism, if it's just a field, then what's the why physical phenomenon are a result?
Not quite understood. I don't understand what your question was there.
All right.
Restate that.
Without mechanism, what's the justification for waves, fields, energy existing?
So that's a question you might ask to the mainstream, right? How can, if there's nothing physical, how can a wave exist, right? Is that what you're basically saying?
Yes.
Yes. Well, the mainstream people would probably have to shrug their shoulders and say, but logically, I mean, what us physicalists would like to say is that, yeah, there's a medium in there, and that's made out of something, right? Because that's the way that logically makes sense, is that if we observe a wave, like I said, the logic is that we observe a wave, therefore, even though we can't physically, experimentally detect anything in there, that there must, in fact, be something physically there, right?
If I may, can I be heard?
Yeah, we can hear you, James.
Oh, okay. My browser said that the mic was lost and I had to restart or something, but thank you. Partly in defense of Mr. Dr. Lucas, Franklin saying that the soliton is not prominent in physics books and so on. Well, there is such a thing called the magnetic dipole moment of particles, including the electrons. And what is that? Mathematically, it's simply a current going around a perimeter. Gee, that sort of sounds like something that Bill Lucas would like to talk about, the soliton. So the premise or the statement, I just like to add a shadow of doubt to the statement that Bill's soliton idea is completely foreign to mainstream physics. Open up any basic physics book, even going back before quantum mechanics to classical physics, those old books that we would read 50 years ago. The idea of a magnetic dipole moment, which by definition, mathematically, is the current, a current of charge going around a perimeter, okay? And that's basically what a soliton is all about as far as the math that Dr. Lucas is using, as far as I understand it. So I just wanted to add that little point. Thank you.
All right. So, does anyone else have any comments about that? I see we have J3.
Well, first of all, we know how to make an electron out of solitons, and we make them in the laboratory. It takes 3 solitons to make an electron. And the soliton has a charge of E/3. And the proton takes more. And so we know what the structure is for all known elementary particles. We can predict from the soliton model the way they decay, the way they interact when they hit each other in a beam, and all that kind of stuff. But can you do that with your type of
equipment? Well, once again, this is going back to the super ultra repressed theory of solitons, right? Because there's no physics books that would ever confirm that. So it's either that it's truly been suppressed, or it's not supported.
It's not been suppressed. I just got through saying that there's such a thing recognized in mainstream physics books.
Yeah, there are magnetic dipoles.
Electron magnetic dipole moment.
Yeah, but that doesn't, to me.
So it's not repressed. It's right there.
No, that's not a soliton, at least not in the way that Bill Lucas observes that.
The math is the same. Show me where the math is different.
The math maybe, you're just talking about the math of fields, right? So, but that's not saying that there's something which is physically there.
This is classical electronics, okay? This is
yes, that's classical electronics.
You can go back 50 years.
I accept all the experimental observations that are associated with that, but none of that to me indicates that particles are made out of smoke rings. So that's where I disagree with that. I would disagree with the assertion.
Well, gee, I've looked at the equation and I've never seen the word smoke ring in any of the equations.
Yeah, and you haven't. Okay? That's because it doesn't.
What are you actually talking about?
If you look at Bill Lucas' theory,
the equations up, understand what the equations say, or we can debate what they say, but each term in those equations has to be defined somehow by the experimentalists. We have the thing called the Bohr magneton. It's listed in the code.
I would like to hear you actually discuss this with Bill. I have to go see what's going on with my mom right now.
This is mainstream physics all the way.
So I have to go see what's going on with my mom right now. So,
okay. So to say that what Dr. Lucas is talking about is completely non-mainstream, yes, certain of his work apparently has been suppressed. I accept his word on that. He's stated that, and I have no reason to. But the fact that it's entirely mainstream physics, 60, even 100, okay? Well, when I was reading every book on electrodynamics, trying to figure out what in the world they're talking about. So this is not a new idea. It's been in physics for decades, up to the present. It's not something that's not in the mainstream. And the prominence, I guess, and the way Dr. Lucas has used this to derive some values, which I'm very interested in, I find to be very important. And I think that Dr. Lucas's work is related to my work. And so I have a bias there, which I'll state up front, because the electron in binary mechanics consists of 3 spot units, which contain 3 fractional charges, 1 each, and they revolve around. And on that basis, I was able to derive from first principles of space-time energy quantization the electromagnetic moment. As far as I know, no one has derived that from first principles, without involving any other measured constants. So that's just a little bit in defense of Dr. Lucas.
If I may interject there, maybe supplemented, getting back to this suppression business. Now, again, I've no particular reason to doubt that. But what has struck me is that there's an orthodoxy in science. I mean, we dissidents should take note of this. There's an orthodoxy in science which traverses all cultures. I mean, you have the sort of culture maybe in the United States where there's complete separation of church and state, as Bill says, but yet the majority of people are sort of religious. You have a country system in Europe where there is a closer relationship in many countries between church and state. You have established churches in some states, but most people in Europe are irreligious. They don't believe in conventional religions. You have the communist, you have the old USSR system, which was ostensibly atheistic. You had the old communist system, which before the present development, they all believed in special relativity without any doubt at all. They didn't believe they didn't have solitons in their physics books. They didn't have any dissident views. You couldn't find anything about the Sagnac effect in any of the books. So what I'm saying is it cannot be as simple as to say that a certain group in the United States just suppressed everything, because then you would have had during the Cold War its arch enemy, the USSR, saying, isn't it terrible what they're doing in the United States? But we, in the Russian books now, have the opposite. The Russian books were exactly the same as the American books, even though they are almost at war with each other. So I've been amazed as a dissident how in completely different cultures in the world, you've had an orthodoxy in science and particularly in physics, which is really the same, which is quite, and I think that's something we should take a special note of.
This might be a point for me to raise an idea, if I may. That
I don't hear comments on it.
that some of the dissident science things that are discussed here, I'd like to just throw out to the group the role of Voltaire in popularizing the work of Isaac Newton. And perhaps what we need is some good publicists. I put out 2 videos recently, not to advertise that. You can look at that if you want. But more as a publicist to publish, to present to the public in an effective and even entertaining way, perhaps, some of the ideas of binary mechanics. So that perhaps some of us here, including myself, are in need of a Voltaire to help popularize our notions.
I didn't really understand that. What was Voltaire doing? I mean, we're trying to popularize
the apple on the head.
We're trying to popularize our notions through Facebook, and now we have the internet. And the internet is probably, the most direct source of access now for dissidents, right? Just like 50 years ago, if you wanted to publish something, you would have had to actually get it physically published by one of these peer-reviewed journals, and no one would ever do that, right? But nowadays with the internet, we can put out our ideas just instantly to everybody, but it just turns out that no one still cares. So it's like, your stuff is out there. My stuff has been out there for 15 years and nobody cares. And probably you kind of feel the same way, right? It's like
maybe we need a Voltaire. Now maybe some of the others here can educate me, because I read, I don't know, many decades ago that Voltaire played a role in popularizing the work of Isaac Newton, which helped disseminate the work of Isaac Newton. And is that correct, or did I just read some nonsense years ago?
Well, I think I read, Jim, that he did promulgate the idea of the apple falling on Newton's head when he was sitting under a tree, and that led to some doubt as to whether it did actually happen. But it appears whether it fell on his head or whether the apple fell beside him, it appears there is actually historical evidence for that. But you're right in saying that Voltaire did popularize the stories. And I think maybe might be the other week. I'm not sure if you were here yourself, but we had David de Hilster here, as Franklin would tell you. And I mean, I've been in correspondence with him. I consider him as a bit of a popularizer. In fact, he's contrary to me in this sense, and I think perhaps his ideas are superior. I tend to be a bit of a person who says, look, if people are not interested, I'm not a missionary. I'm not going to tell them. They'll have to come to me and ask me. And I want to hide our light under a bushel. But David is a more pragmatic person. He says, look, let's go out to the highways and byways. Let's indeed be a Voltaire in your own terms. So he's doing that with the Science Woke websites and so on. And I say good luck to him, and I'm trying to help him and so on. However, I must confess to being rather doubtful about the whole enterprise. I mean, as Franklin says, we've had all our papers there, and people say, so what? People have already made up their minds for whatever reason. And I've said in all cultures all over the world that there's a certain scientific orthodoxy in physical science. And there may be partly elements of conspiracy in it. There may be partly elements of psychology or what people want to believe. But whatever it is, there's this orthodoxy. And it doesn't matter how much evidence, how much rationality you bring to bear upon it, how much you show that they're illogical and they're not using logic, it won't make any difference. Now, people like David might say, well, just by hammering for as long as we can, we'll ultimately get through. I think on one extent they were quoting George Washington, that the truth will ultimately out. I don't know. Perhaps it will, perhaps not. Perhaps we should.
Well, what do you say about the need for, or what I was saying about the need for someone to effectively popularize some of the ideas, say, of Dr. Lucas and others here? And what you're saying, that there's a structure in physics, which, in what I call the physics cartel, which just means monopoly, cartel. Probably the people here are aware that a biologist at the University of Vancouver, her contract there was terminated abruptly after she published her observations that polar bears were doing quite well, thank you, even in spite of the climate warming propaganda. So here she was just fired from her job for opposing. So what Dr. Lucas has said on a number of occasions, and what Ian was referring to also, I think, is that yes, there is a very tangible effort to control and elicit obedience from people in the scientific community, particularly if their paychecks depend on the physics cartel. Like you're a member of a physics department, which has left-leaning, generally chairmen or chairpersons, or you're in one of these huge collaborations of hundreds and even thousands of research workers in dozens of different countries working on projects at CERN and other places. Full stop.
Well, I might mention that my work has been well received in some countries that take a different view towards science than we do. For instance, in Russia, they do science a totally different way. If you want to get a grant to study something, you have to already have done the work and come to valid conclusions to get the grant, and then you publish it, and then you take that money and you've got to do the next project you want to do. But the government is interested in practical things. In other words, if you have a theory that's new, what can it be used to do? Well, I've been working, for instance, with Boeing, and we have a type of inertia that you can get that doesn't require you to use rockets and stuff like that to put satellites in space and all that kind of stuff. You can do it with making inertia artificially, electromagnetically. And they're doing it. They have satellites up, hundreds of satellites already using this, but it's not in the physics books. But there are people that want to do it because they have a need, they have a practical need, they have for it. So they will go after whoever it is that can explain how to do it. And so if you have a practical use for your theory, then you will eventually get it accepted. But if there's no practical use for it, it may stand there for a long time, and not too many people pay attention, even though it might be valid. But and that's what Galileo had a problem, with when he had the theory of the solar system, and people didn't want to believe it. They wanted the Earth to be the center of the universe. And
well, good thing they don't burn people at the stake anymore. Because we'd all be barbecue by now.
right.
They just fire you.
They figuratively burn you at the stake.
Yes, by firing you. Yes, that makes sense. Okay.
Not literally. But I mean, I participated in 2004 in one of the space-time gravitational conferences that were run by the Baltic State University in St. Petersburg in Russia. And I said to them, at the time, and there was an English interpreter there, but I said, it's interesting that I've had to come to the main country of the former Soviet Union to be able to speak freely about scientific questions. I feel myself restrained in doing that in the West. And paradoxically, in the West, where we praise ourselves in being democratic and liberal and free, and you can say whatever you want, there's actually, a worse. It's sort of a latent suppression. Because if you go against the system, you're a denier, or you're a crank, or you're this. You're dismissed straight away. And our whole political system is based on this. We have a general election coming up here next month, and the politicians from various parties who know nothing about it, they put leaflets into your letterbox, and it's all about, we're going to solve climate change, and we're going to solve this, that, and the other. All the politically correct things to say, we're going to reduce carbon. We're going to reduce carbon, things become orthodoxies, and paradoxically, in a so-called free society, they can actually be more enslaving. Now, admittedly, as you say, that we're not physically bringing people.
Well, or it could be that we're all just wrong, and people recognize that. Would be the other thing. So,
that's possible, but nevertheless, they are
probably more possible than there being a concerted effort to all suppress us. But that's kind of why the CNPS exists, because we will not suppress you. You can talk about all your crazy theories all you want. That's what we like. That's what we like. That's what we enjoy. That's what we encourage. So we may all be wrong, and maybe that's really why no one pays attention to my papers, because I'm crazy. That could be true. But once again, this is the place we can come to discuss it. Now, unfortunately, I'm going to have to cut things off a little bit short today. So I'm going to end the conference now, but invite you all back same time, same place next week. All right. Thanks.
Thank you. Bye.
Bye.